Hey, it's Dr. J. 12.1 today. We're skipping ahead to the introduction to counting. This is a little bit of a review of chapter 1. Let me just start with an example that you might remember from chapter 1. How many different ways could you possibly fill out a 3-question true or false quiz? Now, you might already remember the answer from chapter 1. And that's fine if you already know it. If you already know it, go ahead and write the answer down or think about the answer and listen to what I'm about to tell you because it might come in handy. All right. Back in chapter 1, we didn't really have a lot of methods. The main method that we had was, well, we could do trial and error. That could take a very long time, so try true, 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 and true, false, true, and true, true, false, and try to get them all. Yeah, we call that trial and error. And you're not allowed to have any duplicates. So if you're going through your trial and error and you end up with another true, false, true, that would be an error. And you'd say, oh, I can't have a duplicate. And you would sit here and try to go through every single possibility. In fact, that might be the way that many of you did it in one of our very first lab assignments back in February. And at the time, I just let you do it. All right? I didn't say, oh, no, there's an easier way. There's an easier way. I just let you do it. And as we moved through the material, we got other methods, such as the method of exhaustion. Yeah. The method of exhaustion is to list all possibilities, but you would do it systematically. Yeah, not random like we did it here. This is just, it's too random. I don't have any way of knowing whether or not I've got them all. So I don't know if you remember, there was a systematic way of writing out the different possibilities. Remember when we did the truth tables? There are 3 questions, true or false. So we made 3 columns. And we went through all the different possibilities. True, 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 false, 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 false. And then we alternated true, true, false, false, true, true, false, false. I'm blocking a little bit. And then we alternated again, true, false, true, false, true, false, true, false. So if this is a 3-question quiz, and I were allowing you to fill it out as many times as you want, just guessing. In fact, don't even have to read the questions if you're doing it this way. This would guarantee that you got all 8 possibilities systematically. In fact, you might recall, if there's 2 choices, true or false, and there's 3 questions, then 2 to the 3rd power is 8 possibilities. So there are 8 different ways to fill out your quiz, and using this systematic method, you would guarantee that you would never have the same possibility twice. So notice that each of these rows are unique. There are 8 unique ways of filling out this quiz. So that's another method. Yeah. There was actually a third method. Draw a picture. This is sometimes called a possibility tree. Yeah. For question number 1, there are 2 possibilities. True or false? Then for question number 2, there's actually 4 possibilities. There is the same 2 possibilities, true or false, based on what I just did in question number 1. Here, let me move this down here. And then for question number 3, good thing there's only 3 questions because this tree is going to get pretty big pretty quickly. You have the same true-false possibilities for the third question. So you have 2, 4, 8, possibilities. Now, when you do the tree, it's a little bit tricky. It's kind of like you'd have to read it off the tree. So TTT means that I chose true, then I chose true again, then I chose true again. So this would be the first possibility, number 1. Check. Yeah. The second possibility, I chose true, but then in the last choice, I chose false. So it'd be kind of like going like this. From true to true, and then from true to false. That would be TTF. That would be the second possibility. And so you could go through the tree and you could list out each of the possibilities as a different branch of the tree. Yeah, so this one here would go, first I chose true, then I went to here and chose false, and then finally I went to here and chose true. So that's a third possibility. And then finally this last row, this is the last one where you start with true. You would say true, and then you choose false, and then you choose false. So this gives you the first 4 possibilities on this side of the tree. For the other 4 possibilities, you might notice that they just all start with false. My pen is dead. For the next 4 possibilities, they all start with false. So that's just on the other side of the tree. Possibilities number 5 through 8. If you start with false, let's just do a couple of these. So false, true, true would go false, and then true, and then true. So that would be possibility number 5. For number 6, we would go false, true, and then false. We'd end up here. I might as well do them all. For possibility number 7, it's false, false, true. So you're starting with false, then going to false, and then at the very end choosing true. And then finally, your 8th possibility is just going down this column here. False, false, false. That would give you your 8th possibility. So now we've seen that there are 3 basic methods for solving this type of choice problem or possibilities for a true-false question. There's a better way. And the better way is found in section 12.2. This is called the fundamental principle of counting. Here is the fundamental principle of counting, the FPC. If something can be chosen in A different ways, throughout the lecture today, and probably for the next couple days, whenever I say how many ways, what I really mean is different ways. If something can be chosen in A ways, and something else can be chosen in B ways, and something else can be chosen in C ways, and so on and so on. I'm just going to say and so on one more time. Dot, dot, dot. Then all of these can be chosen in A times B times C times etc. ways. In other words, it's just the product of the number of different ways in which you can choose whatever it is that you are choosing. I'm keeping it very abstract and just saying something. And so now we can redo example 1. There are 3 questions. Each has 2 choices, true or false. So the first thing can be chosen in 2 ways. The second one can be chosen in 2 ways because there's 2 choices for each question. The third question is 2 ways. So this only has 3 questions. 3 questions tells you the number of somethings that you have. So there are 3 somethings. Then we can choose all of these in 2 times 2 times 2. Since we only have 3 things, we're going to stop there, which is 8 ways. And now you have the recipe that I intentionally didn't give you back in chapter 1 and chapter 2 because I wanted you to draw the picture. And I wanted you to list out all the possibilities. And if I give you this recipe, nobody's going to draw the picture. Nobody's going to list out the possibilities. They're just going to multiply, get their answer, and move on to the next question. Well, now you can do that. Now you can, in chapter 12, you can read the question, you can use the recipe, and write down the answers. Okay. So example 2. Notice we are now in 12.2. 12.1 is done. How many ways can you answer a 6-question multiple choice quiz if each question has 4 different choices? In other words, A, B, C, and D. typical multiple choice question test. Some multiple choices we do A, B, C, D, and E. For this example, I'm just doing A, B, C, and D. So you have 6 questions. Yeah, 6 questions. Each one can be an A, a B, or C, or a D. You have 4 different choices. So that means there's 4 times 4 times 4 times 4 times 4. You better need a calculator. You better use a calculator. So that is 4 to the 6th power. And this is the reason why I do not want you listing out all the possibilities. You would probably spend the rest of the semester trying to find all 4,000 different possibilities. So you really wouldn't want to guess because there's 4,096 different ways to answer a 6 question. So each one of these represents one of the 6 questions, and there are 4 possible ways for each question to be answered. Okay, example 3. Suppose you're making your schedule of classes for next semester, and you have 2 choices for your math class. You've got 5 choices for your English class and 6 choices for your history class. Assume that you have to take all 3 classes. Otherwise, I wouldn't ask. All 3. So for next semester, you don't get any electives. You got to take math, English, and history. Well, again, we could go through trial and error and try, math and English and history and list out all the different possibilities. We could make a tree. We could exhaust ourselves with all the different trial and error methods. But now that we have the fundamental principle of counting, the FPC, so by the fundamental principle of counting, there are blank times blank times blank. We have 2 choices for math. That's our A. 5 choices for English. And 6 choices for history. And so altogether, there are 60 possible schedules. 2 times 5 times 6. Much easier than making a list of all the different possibilities and exhausting yourself with them. You have 60 possible schedules of these 3 classes. A pizza place, example 4, offers a $5.99 1-topping special. There are 3 different crust options and 16 different toppings. How many different pizzas are possible? So suppose you want to really impress your friends. You want to order 1 of each type of pizza. There are 3 different crusts, 16 different toppings. You only get to pick one topping. All right. But you have 3 different crusts. So there are 3 different crusts multiplied by 16 different toppings. And so there are 48 different pizzas. Of course, only one topping pizzas, so not very exciting. In the next section, 12.3, we're going to revisit this pizza problem where you can choose more than one topping. It gets a little more complicated in 12.3. So we will revisit this problem in 12.3 coming soon. Okay, so that's the fundamental principle of counting. We can use this process for more abstract type problems, like creating words. So how many different 4-letter words, and I'm going to put the word words in quotes, I'll explain what I mean by that in a minute, can be made from the letters R, S, T, L, N, E, A. 1, 2, 3, 4, 5, 6, 7 different letters. And then a quick vocabulary. When I say words, it does not have to be an actual word. In math, when we say a word, we just mean an arrangement of letters. Is a word. So in math, we have a much looser definition of what it means to be a word. Yeah. So for example, RSTL, that's 4 letters. That's definitely a word, even if it doesn't actually spell a word. Okay. So we want to make 4-letter words. So we have 4 blanks to fill out. These are our 4 somethings when you think about it. You have 7 choices. Okay. Now, it didn't say that I can't use the same letter over and over again. So you could have, R, 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 R. That is any arrangement of a letter. So this is technically a word. R, 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 R. It's R. Okay. So we got to read into it very carefully. So I'm making 4-letter words. I've got 7 choices, and I can repeat my choices. So I always have 7 choices every time. For the first letter, there are 7 choices. For the second letter, there are 7 choices. Okay. So 7 times 7 times 7 times 7. Or you could speed that up and just do 7 to the 4th power. That would be 2,400 words. All right. And this is if repetition is allowed. So for example, SSSS, S, T, 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 L, 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 so on and so forth. You can repeat letters in this process. What if repetition is not allowed? What if repetition is not allowed? In other words, once I've used a letter, suppose I put an R here, Now these guys cannot be R anymore. Yeah. And same thing for every other letter. If you pick an S, well then now you can't pick S anymore. You basically have to cross it off if repetition is not allowed. Well, that would mean that I have 7 choices for the first letter, but then once I've chosen that letter, I only have 6 choices for the next letter. And then 5 choices for the next letter. It's kind of like once you use a letter, you cannot use that letter again. And then finally, for your last letter, you would only have 4 choices. Yeah, when you got to your last letter. Now, it might not necessarily be these 4 letters. It depends which letters have already been used. But you have 7 choices, then you have 6 choices, then you have 5 choices, and then you have 4 choices. So this one would give you 7 times 6 times 5 times 4, 840 possible words without repetition of any letter. So the same letter cannot be used twice in this example. You get a lot less words, right? It just dropped significantly. Sometimes we like to invoke more restrictions on the creation of words to try to get a little bit more like English, where you actually have some rules to how you can create a word. So suppose you want to make 3-letter words chosen from the letters A, B, C, D, E, F, and G. Okay. If there is no condition, no conditions imposed, basically anything goes. You can do anything you want. You can use the same letter 3 times. You can use one letter 2 times and another letter 1 time. Basically do whatever you want to do. That's the simplest answer. That would be, again, 1, 2, 3, 4, 5, 6, 7 choices again. This time it's a 3-letter word. So that would be 7 times 7 times 7. Or 7 to the 3rd power. 343 possibilities if there's no conditions. That's the easiest possibility. If I say no repetition, then it would be 7 times 6 times 5. Because once you've used a letter, then you lose that choice. So for the next letter, you only have 6 choices, and then for the next letter, you have 5 choices. So that would be 210 possibilities. Okay. So again, if I say no conditions, I mean repeats are allowed, because there are no conditions. Suppose you say that each word must start with the letter A. Yeah. Well, if I tell you that each word must start with the letter A, that means you have no choice. No choice actually means one choice. So you already have chosen A. It's funny that in English when we say you have no choice, well, none means one. It means you only have one choice. You have to do that thing. So that means that that number is going to be 1. because you have one choice. And then you have 7 choices for the next letter. And then you have 7 choices for the final letter, because it doesn't say that we can't repeat. It just says that it has to start with the letter A. So that would be 49 possibilities, 1 times 7 times 7, if every word had to start with the letter A. What if I said the second letter must be a vowel? Now it's getting a little bit tougher. So I have the second letter must be a vowel. Using these letters, there are only 2 vowels. The first and the last letter, I still have 7 choices for the first and the last, but the second letter, I've only got 2 choices, A or E. 2 choices. So that would be 98. 7 times 2 is 14. 14 times 7 is 98 possibilities. Just double checking. What if I said the last letter must be a consonant? Consonant? Not a vowel. So if the last letter must be a consonant, you have 5 choices for the last letter, because there are 5 consonants, B, C, D, F, and G. So you have 5 choices for the consonant. Then you have 7 choices for each of the others. So altogether, you'd have 245 possibilities. Okay, example 7 is an application of this system. It's a real world application. In California, a standard license plate, so these are the non-custom, non-personalized plates, just the standard license plate that you would get, would consist of 7 digits, starting with 1 number, followed by 3 letters, and then followed by 3 more numbers. A repetition is allowed. Occasionally you'll see some license plate that has 555 or BBB, or you can even just repeat 2 letters, like AAG or 544 or something like that. So repetition is allowed of any type, anywhere from 1 to up to 3 of the same number or letter could happen. So let's go through the calculation. We have 7 different positions, 1, 2, 3. So we have, for numbers, we have 1 choice of 10 symbols, 0 through 9. So you have 10 choices. Well, you have 10 things to choose this one position for. So you have 10 choices, so 10. For the 3 letters, A through Z, you have 26 choices. 26 choices for the alphabetic letters A through Z. followed by the last three numbers, which you also have 10 choices. Ten times 10 times 10. So this is a lot of different license plates. How many different possibilities are there? Definitely want a calculator for this. 10 times 26 times 26 times 26 times 10 times 10 times 10. You could have probably made this a little easier by grouping together the 10s and grouping together the 26s, but I already did it. And I got a total of, I'm going to just list out all the digits and then I'll read the number when I'm done. $175,760,000 possibilities. And these are all different. Because you can't have two cars with the same license plate number, so we still have some room to go. A little fun fact about California, if you don't already know this, I think you should know this, there are 40 million people approximately in California. And you've got 175 million different possible license plates, so we've got room to grow. My prediction, if I can make one, would be that when the population of California exceeds this number, we're going to have to come up with a new license plate system in the state of California because there'll just be too many people, although not every single person. This 40 million includes, children and maybe people that don't drive at all. But just a little fun fact. This is a lot of license plates before you actually get one that repeats itself. So we've got a pretty good system for a while. Okay, example 8, passwords. Have you ever forgot your password? Suppose a password consists of one letter followed by 5 numbers. No special characters. It gets much more complicated if you add in the hashtags and the dollar signs and all the other special characters. And no repetition is allowed. So you can't go 55555 or 33333 or anything like that. How many possible passwords are there? So in other words, if you had to guess, you had to sit there and hack your password, try every single possibility, what would it be? So a password consisting of one letter and 5 numbers, no repeats are allowed. So 1, 2, 3, 4, 5, 6 characters, kind of an old password. This might have been like 10 years ago when you only needed 6. One letter, so you've got 26 choices for the one letter. 5 numbers. No repetition allowed, so that would be 10 times 9 times 8 times 7 times 6. So each time you choose a number, you have exhausted, you've used that number up. You can't reuse that same number again. So this will give us the number of possible 6-digit passwords with the first digit being a number. You get 786,240 possibilities. That's a lot of guessing. And this is for a very simple password. These types of passwords have been cracked probably 20 years ago. They had computer programs that could already crack these types of passwords because the computer would just sit there and try every letter, until it went through the whole alphabet, and then all of these different possibilities. And within 5 or 10 minutes, a computer program could have hacked this. And that's why if you get frustrated with your passwords needing special characters, and there's all sorts of rules, and they might even get longer. I think the other day I was doing something, I made a password, it needed 12 characters and 2 special characters, and oh God, it was ridiculous, and I'm never going to remember that password. So, another example would be a PIN number. So suppose your ATM PIN is 4 digits, 0 through 9. Repetition is allowed. So you are allowed to have your PIN number be 11111 if you really want. All right, how many possible pins are there? How many different pins are possible? So I might write out the entire question. So your typical ATM pin is 4 digits, all numbers because you're using the keypad. 0 through 9, so you have 10 choices. This one's pretty easy. Repetition is allowed, so it's 10 times 10 times 10 times 10. That one's easy. You can just do that one in your head. That's 10,000 possible PIN codes. So that means that the PIN system is very hackable. That's why you definitely don't want to be losing your ATM card, because it would only take a computer 2 minutes could crack 10,000. A computer can calculate 10,000 possibilities in under a minute, or under 2 minutes at least, or at the most. So definitely PIN codes are very crackable. Hackable. Hackable? Crackable? What do you call it? All right, well, we're getting towards the end of it. I kind of want to end with where we started this chapter. Remember, we started this chapter talking about different arrangements of things and people and other types of objects that are being moved around. So in example 10, suppose you have 5 married couples. And they all sit in the same row of a movie theater. Two questions. A, how many different arrangements are there? Remember this one? We did this in the first week of class. They might not have been married couples. I think it was a family, and they were lined up for their photo, right? And we said, how many have this family? And they want to line up for a family photo. And this is basically the same question, except for instead of lining up for a photo, they're all sitting in the front row of a movie theater. How many different arrangements are there of the 5 couples? And then B, how many arrangements if married couples must sit together? So in my first question, you can take these 5 married couples and scramble them any way they want. All the men could sit together, all the women. You could alternate. You could just put them in any possible order. There's no rules with number part A. But with part B, I'm insisting that the married couples must sit together. Okay. Now, people are a lot like numbers in the fact that they cannot be reused, right? So think of a person as being like a number that is unique. And so once you've used that number, you can no longer use that number again. All right. So even though I don't say it in this question, it is implied that repetition is not allowed. All right. It's implied by the fact that these are people. Yeah. So anytime I give you a problem with people, it's implied that people cannot be repeated. You can't sit in 2 seats at the same time, all right? So we have 5 married couples. That's actually 10 people. Yeah. So there are 10 different people at this movie theater. So they're going to take up the front row of a movie theater. Let's see if I can get all 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Almost. Here, let's just do this. So here are my 10 seats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 people. There are no rules. So for the first seat, there are 10 choices. Once that person is sat down, there are only 9 choices. Once that person is sat down, there's only 8 choices. You see the pattern? It keeps decreasing down to the last person. Oh, I missed 4. Almost missed 4. 4 times 3 times 2 times 1. The last person really has no choice. But remember, no choice means one choice. I don't have a choice. That's your choice. All right. This is also called 10 factorial. Some of you might have a factorial button on your calculator. If you do, you can use that button on your calculator. For my calculator, it's the second function. I hit the second key. And then I hit number 3. That's my factorial button. And that gives me 3,628,800 possibilities. One way to think about that is, you know, if these people had an all-you-can-watch movie pass or something, they could go to 3,628,000 different movies and never sit in the same seat twice, at least not in exactly the same arrangement twice. So it'd be a new arrangement of these 10 people every time. It's the same question as the family photo that we did back in chapter 1. Now, if married couples must sit together, that's like taking 2 seats and bundling them together. That's like taking 2 seats and bundling them together and saying, oh, you have to sit with your spouse. So these 2 people have to sit together. They can't move around. Okay? So it's kind of like thinking about this as only being 5 people, if you think about it, right? You have 5 people, and each one of these has 2 different ways that it could go. Let me draw this out a little more clearly. So if the couples must sit together, So if the couples must sit together, that's like bundling together two of the seats and saying, well, these two seats are occupied by a couple. These two seats are occupied by a couple. These two seats are occupied by a couple. Two more. Oh, no, I drew them too big. Sorry. I'll try it this way. There we go. So I got two seats in each box. Okay. And there's 5 couples. Yeah. So initially you have 5 times 4 times 3 times 2 times 1. Or in other words, you have 5 factorial. So what's 5 factorial? You can probably just do that on your calculator. 5 times 4 times 3 times 2 times 1 is 120. $120 possibilities if you think about each couple is treated as one seat. Yeah. Each couple is treated as one seat. There's only 120 possibilities. Now, however, there's a subtle thing that we have to read into. They could switch. You could have person A and person B could sit there, or you could have person B and person A sit here. Yeah, they could switch seats with each other, and they're still sitting together. So each of these has 2 more possibilities. Yeah. So there's 2 possibilities for that. Yeah. And there's 2 possibilities for this couple as well. CD, or they could sit DC. EF, or they could sit at FE. So each couple has 2 choices of where to sit. So we need to multiply each one of these times 2. Yeah. So 2 times 2 times 2 times 2 times 2 is 32 multiple options. So the total, I have 120 ways that the couples can take their paired seats, and then within that, there's 2 times 2 times 2 times 2 times 2, 32 different ways in which they could sit in there. So 32 times 120 gives us a total of 3,840 possible if the couples must actually sit together. I have to admit, the first time I did this problem, I just stopped right here at 120. And in my mind, the first time I did it, I just thought each couple sits down and that's it, it's over, right? But then you have to stop and think about it. Well, wait a minute. It doesn't say that once they sit, that's their only choice. So you have to consider the second set of conditions, which is that each couple has these extra 2 choices of where they're going to sit. Okay. All right. That's the end of the section. So Dr. Jordan signing out. Bye-bye.